Hi, I'm Wim Blodgett, President of Holland Pump. I'm joined today by our Director of Operations, John Hamilton. I'd like to thank Amy Fletcher, Director of Marketing, for facilitating this webinar, and I thank you for attending today. After a 13-year career in residential and commercial construction, I joined Holland in 1999 and became president in 2007. Today, we're going to talk about how to select the correct pump for your application.
Hi, I'm John Hamilton, Director of Operations. I joined Holland in 1997 and oversee service operations in our 10 locations in Louisiana, Florida, South Carolina, and New York. Centrifugal pumps produce head and flow by increasing the velocity of the liquid with the help of a rotating vane impeller. Positive displacement pumps operate by alternating or filling a cavity and then displacing a given volume of liquid. So diaphragm pumps are an example of what are known as positive displacement pumps. The way they work, as the diaphragm starts downward, the suction flapper closes and the discharge flapper opens, allowing the water in the pump to be discharged. Diaphragm pumps advantages are they're dry priming, they can run dry, handle air and water, handle most solids, handle abrasives, no rotating parts in contact with the fluid. The disadvantages are low capacity, low pressure. At Holland, we have two sizes that are available in 4 and 6-inch skid and or trailers.
There's pictured here a well point pump on the top left, and then a cutaway of the pump itself. The general arrangement of the pump is a diesel engine, can be an electric motor with a gear reducer, and then the pump. The fuel tank is sized to run the pump 60 hours continuously without the need for refueling. Below the control panel, you see a little canister there, with a white lid. That's for an extra fuel filter, which comes in handy. The pump has shutdown protection. Many of the pumps are fitted with our HANS system, or Holland Automatic Notification System. It's a pump that cannot run dry for very long, so we have a shutdown system. In rotary pumps, a low pressure area is created when rotors separate. The liquid is forced by atmospheric pressure and is carried around the housing as the lobes rotate. One lobe does not mesh with and drive the other. This is accomplished by using an external gear set. Advantages include being highly efficient and low fuel consumption per gallon pumped. Can handle both air and water. Disadvantages, as I remembered, can't run dry by itself, although we do have shutdown mechanisms to prevent the pump from burning up. They have limited solids capability and limited applications for us, well point and sock only. However, the manufacturers of these pumps typically use them in many applications, pumping thick material like drilling mud or glues and so on. But for us, the primary application is well pointing and sock.
All right, here you can see various types of centrifugal pumps. In the Holland pump fleet, we have electric submersibles, hydraulic driven pumps, and prime assisted pumps. We also offer wet prime pumps. A wet prime pump requires the user to manually prime the pump with water before starting the pump. Prime assisted pumps have several different methods. We use a diaphragm style. We also have mass port, and there is a compressor prime also. The ability to prime a pump is measured in CFMs, or cubic feet per minute. Our trademark prime assisted suction lift pumps is Prime 3. That's because our prime's 3 times faster than many of the pumps on the market because we use a 50 CFM diaphragm priming system. Holland Pump also offers a Massport style vacuum assisted pump that has much higher CFM capability.
In addition, Holland Pump represents many leading electrical submersible manufacturers, including Gorman-Rupp, ABS, Homa, Surumi, and Weta pumps. Submersible pumps are a device that has a hermetically sealed motor close coupled to the pump body. The whole assembly is submerged in the fluid to be pumped and pushes the water.
Wet prime submersible pumps advantage work continuously without failure when plugged into a stable power supply. Electric power is cheaper than fuel. They have low maintenance cost. They're environmentally friendly, less likely to suffer discharge cavitation, and not affected by high altitudes or atmospheric pressure. The disadvantages is you must have a power supply. Many of our locations also have the generators we offer to rent alongside these pumps.
Holland Pump has electric submersibles in many horsepower ranges to handle small solids, large solids, high volume or low head water transfer applications, and high head applications as well. In addition, we have staff members that specialize in providing permanently installed electrical submersible pumps, which typically might require an advanced control panel. One of the originators and leaders in the wet prime market is Gorman-Rupp, which is particularly famous for the Super T and CE series wet prime pumps. The principle of these pumps is vacuum is produced as the impeller rotates and draws air into the pump where it is mixed with the liquid and contained in the pump casing. The air-liquid mixture is driven into the priming chamber where the air separates out and is expelled through the discharge port while the liquid, due to its higher density, falls back and is recirculated.
The principle of priming mechanisms consists of diaphragm pump that creates a vacuum and evacuates air. As water enters the priming chamber and a float rises and presses against a rubber pillar valve and closes off the priming system when priming is achieved.
Holland Pump rents prime-assisted pumps from 3 inches to 18 inches. Typically, these are diesel-driven skids or trailer pump packages that we designed to accommodate pumps manufactured by Selwood Pumps of the UK and Cornell Pumps of Portland, Oregon. Also in 2020, we acquired CDPW Incorporated of Edgewater, Florida. For 99 years, CDPW has manufactured the complete dewatering line of vacuum-assisted trash pumps and wellpoint pumps in 4-inch, 6-inch, and 8-inch sizes. In addition, Holland Pump is a distributor for Gorman-Rupp, Atlas Copco, Thompson Pump, and Wacker-Neuson. Typical features and benefits of suction lift and vacuum assist trash pumps include faster priming, common diaphragm or rotary vane vacuum assist made to prime from a dry condition. So often these pumps are called dry prime. You might hear that term. And they reprime automatically. They're good for open sumping, Kelly wells, sewer bypass, and applications where the pump may lose its prime and is unattended. Often our packages have auto start stop panels. With the Cornells, they feature a run dry cycloseal, and many of these pumps are available as what we call super silent or sound enclosed, both as sound enclosed engines and as fully enclosed.
The CDPW has 3 models of rotary vane priming systems. The smallest one is a C3. It does 65 CFMs and achieves 825 gallons per minute. The C5 is a 130 CFM vane pump and it achieves 1,400 gallons per minute. And the C10 is a 200 CFM pump that achieves 2,600 gallons per minute.
Holland Pump is probably best known for our hydraulic submersible system line. We build systems from 4 inches to 42 inches with a diesel-powered hydraulic unit, and the hydraulic pump is mounted directly to the engine and pumps hydraulic fluid from a hydraulic pump at about 2,000 psi, through a high-pressure hydraulic hose up to 100 yards to a hydraulic pump, which is typically floated on the surface of the water. The hydraulic fluid flows through the hydraulic motor and turns the shaft, and the hydraulic fluid then travels back at low pressure to the hydraulic tank where it is recirculated. A heat exchanger on the pump head helps to dissipate any heat that builds up from the continual recirculation of the fluid. Like an electric submersible, hydraulic pumps push the water.
Holland Pump makes 4 basic models of jet pumps. Typically, priming is achieved by use of a Protec priming system driven by hand. The advantages are a water-cooled diesel engine for efficiency and cost. Fuel and design efficient Cornell pump is rugged and powerful. Maintenance efficient impeller and volute designed to eliminate costly repairs. The disadvantages are they can't run dry and limited solid handle capability. Our jet pumps can achieve 100 to 180 psi. The J 2.5 can achieve 400 gallons per minute and 320 feet ahead. The J4 achieves 600 gallons per minute and 237 feet ahead. And our J6 can achieve up to 1,300 gallons a minute and 375 feet ahead. Some of the most typical pump applications include open pit and quarry drainage, well point dewatering, sock dewatering, lift stations, high pressure pumping, bypass pumping, and trench and ditch drainage. Right here we have a chart with some comparison of each pump. So our double diaphragms we have in 4 and 6 inch. They'll handle solids up to 3 inch, max flow rate of 300 to 400 gallons per minute, a max suction head of 28 feet, and a max discharge head of 70 feet. The suction lift trash pump range from 3 to 18 inch. They handle solids from 3 inch to 4.5 inch. The flow rate range from 540 to 9,000 gallons per minute. The suction head range from 20 to 25 feet, and the max head is 111 to 240 feet. So in our vacuum assisted trash bypass pump line, we have a range from 4 to 8 inch. They'll handle a 3 inch solid. The flow rate is from 850 to 2,400 gallons a minute. The max head is 25 feet, or the max suction is 25 feet, and the max head is 125 to 167 feet. The hydraulic driven submersible pumps range from 4 to 14 inch with a max solids of 3 inch. They'll range from 800 to 6,500 gallons a minute. They don't have a suction head because they are down in the water, and their max head capability is 68 to 160 feet. Our actual flow pumps range from 14 to 42 inch. They'll handle up to 3.5 inch solids. The flow rate on them are 14 to 55,000 gallons a minute. Once again, they're down in the wet well, so they don't have a suction head, but the max head is 26 feet.
Now, depending on your pumping requirements, how many gallons per minute you need to pump, how much head you have, what size solids, and so on. Double diaphragm can be appropriate, as can suction lift pumps, vacuum assist trash pumps, hydraulically driven submersible pumps, and axial flow pumps for open pit or quarry drainage. In this picture in the top left, you see a long line of our D14 model. This is a hydraulic power unit. This was at the Faca Union Pump Station south of Alligator Alley. The project consisted of a 500-foot by 500-foot excavation that was ultimately 45 feet deep. Hydraulic pumps were ideal for this application because for much of the project, the suction lift was over 15 feet, which is an ideal scenario for hydraulic pumps. The picture illustrates some of the advantages of using hydraulic systems. The pumps are located where they can be easily fueled and serviced. By contrast, to get the best performance from a typical prime assisted suction lift pump, which I'm saying to pump at the BEP or to the right of the curve, the pump needs to be located close to the water level to avoid what is known as suction cavitation. A primary advantage of prime assisted suction lift pumps is being able to achieve a lot of head on the discharge side of the pump. So that's when they often come into play and as the first choice.
All right, right here you can see some various types of well point dewatering. A well point system consists of a jet pump to jet well points in the ground, a well point pump which is well suited for handling water and air, and a well point accessory system which consists of PVC header which is horizontally installed on the surface where one connect swings typically every 2 to 4 feet. The swings connect the header to the well points. The well points are typically 1.5 inch schedule 40 PVC with 3-foot slotted well screens at the bottom. Each well point draws water and air in the point, and the pump draws the water from the points.
Another popular method of using vacuum assisted well point pumps and positive displacement pumps is in conjunction with sock. With sock dewatering, the first step is to use a trencher to dig a trench and bury drain tile, which is sleeved with filter cloth. The pump is then connected to one end of the drain tile, and dewatering is achieved by lowering the water table and expanding the cone of influence. An advantage of sock dewatering is that the system can remain in place and used again if needed. For many years, municipalities relied primarily on diesel-driven generators to provide temporary power for lift stations when there is a power outage. The generator would provide temporary power to a permanently installed pumps. About 15 years ago, pump companies started to offer what is commonly called backup lift stations, which typically consist of a sound enclosed diesel pump. The backup lift station provides double redundancy. When there is a power outage, the sound enclosed pump provides temporary pumping. However, most of the time lift stations fail, it isn't because of a power outage. Most of the time lift stations fail because the permanent pump system has failed. So the backup lift station provides double redundancy by providing temporary power temporary pumping when there's a power outage and temporary pumping when the permanent pump system fails.
All right. The picture illustrates a few applications for jet pumps. In addition to installing well points, jet pumps are often used in aggregate plants to wash stone, for temporary irrigation projects like golf courses, and for fire suppression as a mulch plant or a forest fire. One of the best applications for prime assisted suction lift pumps is for bypass pumping, which can consist of bypassing a manhole when pipe is being repaired or bypassing a lift station when a lift station is being renovated. In fact, anytime permanent pumps break or need to be serviced, the pumping needs continue, so prime assisted suction lift pumps are often a great choice for this work. Often submersible pumps and well point pumps are used in conjunction with another. A well point system is installed adjacent to the pump cut to lower the water table, and an electric or hydraulic driven submersible is used to assist and is capable of handling dirty water and trash. Let's run through a real scenario. So what kind of liquid material will you be handling? So dirty, muddy water on an excavation site. We'll go with that one. What is your site like and the purpose of your pumping? Open excavation or trench for new sewer pipeline. What volume are you permitted to discharge per hour? 102,000 gallons per hour. How far away is your discharge point? 15-foot suction lift and 1,500 feet discharge pipe or hose. Can you get to the discharge point in a straight line or are there obstacles or maneuvers around? 8-inch suction hose with 145-degree elbow, then 8-inch PVC pipe horizontal line with 190-degree elbow and 245s. Do you have power dropped on the site? No electric power available remote location. Are there any sound or space restrictions? None. Here's the summary. Dirty, muddy water on an excavation site. Open excavation trench for new sewer pipeline. 102,000 gallons per hour, 1,700 gallons per minute. 15 foot of suction lift and 1,500 feet of horizontal line. 30 feet of 8-inch rubber suction hose, then 8-inch PVC horizontal line by 1,500 foot with elbows. No electric power available, remote location, no specific restrictions on site.
So now that we know all the parameters around the application of what's going to be required to do the pumping, we move towards calculating the total dynamic head of the system. And just to explain a little bit about that, both on the suction side of the pump and on the discharge side of the pump, we have losses due to friction of the water moving through the pipe on the suction side and water moving through the discharge on the discharge side. And one of the things that we need to be aware of is the velocity of the water, both on the suction side and on the discharge side. On the suction side, the best practice in terms of minimizing the wear to your pump is to keep the velocity under 6.5 feet per second, and on the discharge side, about 15 feet per second. And oftentimes because of the length of discharge that is required, we'll play around with, what kind of discharge are we going to use? What size are we going to use, and what material are we going to use? All pipe and hose has pressure ratings. So from a safety standpoint, it's very important, very critical to select the right material so that there's no accident that is created by using the wrong material. We use the Hazen-Williams equation for calculating total dynamic head. This takes into account the materials that you're using, all of which have a C value or a coefficient, friction coefficient. And there's a lot of smartphone applications available that make this easy for you. You can do it by hand, like that's old school, where you consult some books that have tables both for losses of feet per 100 for each pipe size. And in addition, there's tables that show friction loss in pipe fittings. What's shown here is just an example because we actually typically use much larger fittings in terms of diameter. But this gives you kind of an illustration of what's widely available that we consult as we calculate the total dynamic head. And you can see in this chart, if you look like under 400 gallons per minute, what the result is if you're using 4-inch hose versus 6-inch hose, it makes a big difference in the velocity in feet per second and in the head, overall head. So sometimes, depending on what you're pumping, you really need to have as small a discharge as possible to keep the velocity up. For example, if you're pumping some really thick, dirty water that has a lot of solids in it, you don't want the solids to settle in the pipe, so you have to keep moving the solids through the pipe. And in that case, you might decide that it's better to put a lot of head on the system and move the material through the head than risk having the solids settle in the system and cause you problems. This is a typical illustration just to show everyone, what we have to take into account. The first thing is suction lift, which is right there. And that's the vertical distance from the pump to the center line to the free surface of the liquid. Now, you do have to take into account that, if your desire is to lower that water level down, that you take that into account, because maybe you're lowering it another 5 feet and then your suction lift is going to increase by 5 feet. Then also you need to take into the account the fittings that are being used, the 45-degree elbow, the suction screen, and because those have known losses which are added to calculate the total dynamic suction lift. Then you have to also take into account the discharge lift, which is the vertical distance from the pump center line to the highest elevation of the discharge line, which in this case is 20 feet. So the total dynamic discharge head is the sum of the static discharge head plus all the friction losses. So 8 feet plus 190-degree elbow plus 20 feet plus a 45-degree elbow plus 15 feet plus 45-degree elbow plus 1,500 feet of horizontal pipe, all in 8-inch diameter. I'll just speak about one other thing. It's not on the slide here, but great practice with suction lift pumps. Senior Vice President of Sales, Jared Williamson, and I were discussing. It's a great to use gauges. So if you have a gauge on the suction side of the pump and a gauge on the discharge side of the pump, you can just use the gauges to calculate the total dynamic head. If the suction gauge shows a positive inlet pressure, then subtract it from the discharge pressure to get total dynamic head. Otherwise, you add the suction vacuum to the discharge pressure to get the total dynamic head. So to just review, we remember that we were using 1,700 gallons as our customer's desired flow. The flow rate is an essential part of the friction loss calculation. And hoses, pipes, and elbows have all been calculated at 8-inch for the suction side of the pump and the discharge side of the pump. So this is, kind of a typical curve that you might see. And on the left-hand side, vertically, they're showing total dynamic head in feet. And on the right-hand side, they're showing total dynamic head in meters. And on the bottom, on the horizontal axis, they're showing gallons per minute. And then beneath that, they're showing cubic meters per hour. And, this is often done because depending on where your pump comes from, for example, if it's a European pump, all of the technical data on the pump will be expressed in metric. So now that we know how many gallons need to be pumped, and what we are pumping, which is to say what kind of fluid, what size solids, what temperature, what elevation, and we also know how much suction head we have, how much discharge head we have, and what the total dynamic head is. We can consult the pump curves and select the best pump for the application. So the yellow dot is where our parameters lead us, and that turns out to be a great ideal place to be pumping. The black lines show the pump speed. The green lines show the horsepower that's required to achieve the gallons of water being pumped. And the purple lines show the lift that's capable of being handled at that point. And very importantly, the blue lines are the efficiency curve. So at the far left blue line to the far right blue line, that's kind of the overall operating of range of the pump. But we strive to pick a pump where we'll be pumping on the best efficiency point, which is commonly known as BEP, best efficiency point. So you can see if you look towards the center of the efficiency curves, it's 82%, and then it drops off below 75% at the left-hand side of the curve and the right-hand side of the curve. By picking a pump that will wind up achieving the desired duty point, and also the best efficiency point of the pump. We put minimal wear on the pump and at the same time have the best fuel efficiency. We have many of our spec sheets listed on our website and available to download. Typically, the spec sheets follow a standard format. At the upper right, we list the specification section and the release date of the spec sheet. In the first section, we list the details about the pump and the pump materials. This is often followed by a performance table, and that shows the BEP of the pump. That's if you can see it, that's there's about 6 or 7 lines there, and the one that has the asterisk is the best efficiency point. Below the performance table on the first page, we generally describe the specification of the pump driver, be it an engine or an electric motor. Typically on the second page, we have a schematic diagram that shows the pump layout and the overall dimensions of the package. Often we also include the overall weight of the unit as well. Finally, we include a pump curve. For prime assisted suction lift pumps, this will show the performance at different speeds and suction lifts. In Florida, most of our work is close to sea level. So one thing we really didn't talk about today was making adjustments for altitude. But Earth's atmospheric pressure is 14.7 psi, and every 1 psi translates to 2.31 feet. So a perfect vacuum at sea level would be 33.95 feet. Pump curves will often state a net positive suction head required, or NPSHR. And the inverse of NPSHR is NPSHA, or net positive suction head available. In general, with prime assisted suction lift pumps, when we pump to the extreme right of the curve, the NPSHR increases. This means that in order not to damage the pump, the static lift must decrease. So, you'll see oftentimes a pump and it's working, it's pulling 20 feet, but you'll hear a loud popping noise. And when you discern that, what you're hearing is suction cavitation, and that will damage the pump impeller in short order. Depending on site conditions, putting the pump close to the surface may be possible, but it may be difficult to fuel, or it may have the danger to wash in, go underwater. If there's a pump failure and it doesn't have a lot of other pumps working besides it doing the same activity, if the application is relying on 1 or 2 pumps and one pump fails and the water is rising, it doesn't take too long for the pump to go underwater. Another thing to always be concerned about, especially in Florida, especially this time of year, is rain events. This is just an example of a tool that we use internally, a spreadsheet tool, where a pump consultant can plug in all of the parameters for the suction side of the pump and the discharge side of the pump, and play around with using different diameters of pipe to get to a dynamic, total dynamic head that works well with the curve. In summary, there are many types of pumps from which to choose. Choosing the right pump is really critical for the job. I always say that pumping is often, a very small part of the overall budget for the job, but doing the pumping right really can affect the job schedule in a dramatic way and save a tremendous amount of money for customers. Having the answers to a few key questions gets you on the right track. There are guidelines and pump selection calculators to help you design your system, and please visit our website for more information on pump selection. Any questions or comments?